We might come across as well with some functions expressed as a piecewise function just like this. For this video, we are to verify or to check if the given function expresses a piecewise function, sine z over z if our z is not equal to 0, and 1 if z is equal to 0, is continuous at z equal to 0 or z sub 0 equal to 0. So this time, we're still going to use the three conditions to be satisfied. If we can satisfy all of them, then we can say that this is really continuous, or this piecewise function is continuous at z sub 0 equal to 0. So the first condition, let me rewrite here the function to make it bigger. Okay, you have here the situation sine z over z, that's the definition of the function, if our given value for z is not equal to 0. But if it is equal to 0, we pick the value of 1. Okay, so again, at z sub 0 equal to 0. So let's start with the first condition. We need to show that the limit of your f of z as z approaches to z sub 0 exists or must exist. Okay, so for this type of situation, we're talking about our z sub 0 at 0. So which of the two definitions of our piecewise function will be used? The question here is, when we talk about the limit, it doesn't approach to 0. That would mean we will be using the first statement, because this is the function defined if the value of z is not equal to 0, or even those values that is actually approaching to 0. Okay, so we are going to use here the function, the sine z over z for our first condition. So that would mean, let's verify if the limit of your sine z over z as z approaches to z sub 0, or in this case, our z sub 0 is already identified as 0, if it exists or it has a specific value that is acceptable in the realm of complex number system. Now, you could of course try to look into this as the possible values approaching to 0. But take note, we are on complex numbers now. It's not enough for us to really write or predict the value of a given function as it approaches the value of z sub 0 from the left and from the right alone, because it could actually approach that value in many directions. However, if you can still remember a portion of our discussion in the calculus, if we have here the limit of your sine x over x as x approaches to 0, which is similar to this, but instead of x's, we're using z's. This is just equal to 1. This is an identity that we have learned when we studied calculus. Okay, we have the limit of sine x over x as x approaches to 0 is equal to 1. There is also a video for that in this channel, specific playlist for the calculus, because we also tried to verify this to be true. And since we had that already as part of our previous discussion here in this channel, let's just automatically claim it to be true here. So we have the value for that equal to 1. And since 1 is a value that is existing, this is already been satisfied. Pardon if I'm not going to show you the derivation for that. Again, you might want to check the description below. I'm going to place there the link to the video discussing this on one of the playlists in our channel as well, because this is already accepted to be true. Okay, because if we're going to substitute 0, sine 0 is 0 over 0, so it's actually indeterminate form. However, if we're going to look at the values from left and right direction, so we will have the value which is equal to 1. Okay, but I mentioned that if in our complex number system, it doesn't just require left and right, but this works in the same manner. Okay, so for them to have the same value of 1. With that now, let's proceed to our second condition. The second condition, if your f of z sub 0 must exist. Okay? When would this be possible? So we're going to use now your f of 0 as this is the value of your z, and what would be the value of the function? take note, we only have one description there that would accept 0. That's your second statement on our piecewise function. If z is equal to 0, automatically the value is 1. No need for substitutions, because based on the definition of this piecewise function, once z is 0, the value is 1. So once we have here f of 0, we have here 1. And since this is a number in a complex number system, the definition or the condition number 2 also is satisfied. Now with that, let's proceed to the third condition, and this establishes this reality that the limit of your f of z as z approaches z sub 0, which is the first condition, and it is existing, must be equal to your second condition, f of z sub 0. This is only possible if the first two conditions have been met. If one of them or even both of them are not satisfied, definitely we don't need this third condition. And this third condition, if we're going to try, would obviously not be the same or not satisfied if the first two are also not existing. The first condition brings us 1, as mentioned. That's part of our calculus identity. And the second condition is also 1. This means the third condition has been met. With all of these three are true for this given piecewise function at z sub 0 equal to 0, again, considering this to be true already, we can now say, hence, or therefore, the function f of z equivalent to your piecewise function sine z over z if your z is not equal to 0, and 1 if z is equal to 0, is continuous at your z sub 0 equal to 0, because we have all of this being satisfied. Okay, that is for this video, and probably the last example on the verification of whether a certain function is continuous at a given point. The next few videos will focus on some points of discontinuity, because if there are possibilities, just like in the previous video before this one, we have established that that function was actually discontinuous. So we are to identify in the next few videos what are the points of discontinuity, or when or where or at what values of z our function will be discontinuous. And that is only possible for discontinuous functions, not this one, because this example in this video is already continuous. Thank you very much for watching.